do is we'll like voice act all the characters.
That's really funny.
And there's a character who my friends and I have decided is a Scottish accent. I have a really shit Scottish accent. And so my friends always are like, it's time for Maggie's bad Scottish hour, where I just talk to myself in Scottish, basically.
That's really, really funny. My girlfriend was convinced me to start playing Factorio with her.
Hello.
Oh,
Morning.
yeah.
Told me not to touch Factorio until, do you know who Dave is? He's one of the tutors in the Julia Center.
Does he know yours?
Yeah.
Okay, yes, I do know.
They need to, there's literally
Oh, for which thing?
I was just asking.
Oh, there are a lot of.
I think I turned in all my stuff. I just wanted to check.
They have at the house.
There's probably more that I have, but I'm giving up toting them.
I know I have all my labs. So
That's me with like, all, cause like, Final Fantasy 14 is fun, there's like so many things to do. And you can get into really like difficult like dungeons and stuff like that. And everybody who has US all agrees. The true purpose of playing the game, the true end game,
I have a lab that I have yet to turn in, but I was wondering if I could wait till after the
that's why
test.
people play.
Yeah.
Outfits
Yeah.
and also like houses. Cause you can like buy a house and decorate it all you want, and it's so fun. And I've spent so many hours doing that. I've had so many friends be like, you know, Maddie, I think you would really like The Sims. Like, you just play Final Fantasy 14 so you can play The Sims. Like, you just play The Sims. You don't have to do it this way. And I was like, I would, but I know if I download The Sims on my computer, I will never see the light of day again.
More part of the big picture than
Yeah.
anything else.
I am like, I like video games, but I'm very picky with like the games I like.
Get it out of the way.
Legend of Zelda. Like, Hyrule Warriors.
So more like kind of JRPG type games, or like open world JRPG.
More like, I really like hack and slashes. Like, play a first person shooter.
Do you know anything you really like? It's a hack and slash game.
I love these.
Math
I've played all of their games and I love super
Yeah. Did you see that they're making a Hades sequel?
It's coming out next year. So this year.
Then, you might like this game. There's another like 3D inspired game that came out recently called Stray Dogs. It's a choose your own adventure musical.
Oh, I love musicals.
But anyways, you like you either like make choices while the song is going, and your choices affect the song.
Oh, that's
Gone to see
like difficult to do.
Oh,
Like
yeah.
to write a song that has like
Yeah.
so many different like versions.
No, it's so good. It is so good.
You said it was Stray Dogs. I'm writing this down.
It's like $30.
Calculus 2. I think I can do it, but it's gonna be really hard. It'll be hard. If I still have to figure it out.
I love triangle stuff. I love triangle symbols and all that jazz.
In pre-crowd.
Statistics? That's very different. Never math.
Do you know if they have to take statistics for anything?
So this is
I have no clue. I'm not.
in high school. Yeah.
Who's who? Who's taking what major?
Right.
I was going to do calculus, but then
Well, I'm pretty sure the major things are different
an
depending on
online
what
school
college
thing,
you're in.
and there was no calculus. I had an online
Yeah.
Look at the major plan for the college you're going to.
They're required.
And you assume that assume that I already know where I'm going. Then again, I'm not doing it.
I'm just ticking. If you're going this year, you have maybe applies.
Oh, no, applications don't open until January
Yeah.
for the program I'm doing.
I know that it might finish in like May. And then
You can select like when you're ordering transcripts, like wait to send them until after grades have been posted.
or they'll just like for mine at least. Yeah. That's a good one. For mine at least it just I just applied and sent unofficial transcripts and then they said whenever you get to it, basically send all your transcripts like over the summer and stuff when you're done.
What college are you transferring to? Okay.
You know they're not going home.
I have one anyway. I'm applied for 4 transfers. When I went back, like, visiting my mom and my sister. I've been planning on it since high school. I applied for the 4-year form. Well, my friend got it. Like, normally they put it in the seat or something. It'd be nice. They pay rent, they give you allowances, they pay 90% of your tuition. They pay your food bill.
That's what I could have done.
I think the food is only for
whatever reason.
food court stuff.
Yeah.
On my senior year, literally the only class I actually had to take was secretary class. And then I have to take 0.01% of elective grants.
It's that you have to be a transfer student and
We did this at
you have to have above a GPA 2.5 or something.
but it counted
You
as
have
like
to
0.8 of the credit or something.
show that you're like
So I still needed to take another elective class to get it.
really well. Pretty similar.
All right, let's go ahead and get started. And so I'm sorry I had to cancel last Thursday. I usually never cancel class, especially not the last official lecture day, but I was super sick and couldn't get out of bed. So we're gonna go over what your final is over today, and then we'll kind of pop back over a little bit to the lecture and just finish up kind of what you need to know. We'll talk about what we'll probably save till next term, and then keep doing review problems. And then, of course, ask questions. All right, sorry, I have too many tabs as I have your exam here, so I can reference it, so I can tell you all about it. So as it stands, it is 11 questions, except one of them is a bonus. And it starts off with 6 multiple choice questions. And so I would expect naming, so that's a good spot to ask about that. And then the different definitions, like what is a state function type of thing, or versus not a state function. So do we remember?
State function is.
Or an example of a state function?
State function is things like that depend on the change in the reaction, right? Like pressure and volume.
Well, it's we just say like usually not path dependent is a more broad term.
Yes, that's the term.
So not path dependent. And so enthalpy was our example of that. let's see, so also we would test about types of reactions. Oops. So, right, single replacement, double replacement. Did you have a question
I
or?
had a question about the state functions. I wasn't there for a lecture, but I did watch the recorded lecture. I wasn't sure, I don't remember if you mentioned, what exactly does like path dependent mean technically? Because I never really got exactly what that meant.
So that would be like work, right? So then work is path dependent, so it depends like, right, how, like where are you exerting the work and then how long is the path, right? And then there's like certain definitions of what work is. So that's where the path comes into play. And so same thing with heat. Heat is also not a state function, so these are not state functions. And so heat, again, that depends on the path that you're doing, you know, what's going on, what type of reaction. So those are path dependent, while just the overall change in enthalpy is what we're measuring, so that's a state function. And other things, right, entropy. So we haven't talked about entropy, but entropy would be a state function. Internal energy is a state function. And then, yeah, pressure, volume, temperature. But we've only, our main focus was enthalpy. Does that clear up state functions? Watching the chat too. All right. And probably also there's precipitation reactions potentially. So like what precipitate forms. So precipitation prediction. So just make sure, right, you have your little solubility chart. So kind of think of what what resources do you need to have. And could be some limiting reagent question. And so let's do one type of question. So we could have, what sample has the greatest number of molecules? And so our choices are 5 grams of helium, 5 grams of argon, 5 grams of krypton, and 5 grams of xenon. So take a minute or so, and then we'll go through it. So watching the chat for answers too. Let's see, what are we thinking? What? So helium, thumbs up, thumbs down, what are we thinking? I see, yes. And so excellent, right? So we just had to compare, so our 5 grams divided by molecular weight to give us moles or molecules. And so whichever was the smallest. All right, so let's try another little practice problem. So what sample has the greatest number of molecules? And let me blow that up. And so our choices are 5 moles of helium, 5 moles of argon, 5 moles of krypton, 5 moles of xenon, or all the same. So what are we thinking for this problem?
They would all be the same, right?
All the same, excellent. So they were all given in moles amounts, so all the same number of molecules. All right, so then let's talk about where we kind of left off on our chapter 14, because this will be on the test. So we were talking about breaking bonds. So breaking bonds requires energy. Making bonds is exothermic. And I'll talk about the biochemistry bit and how it all.
Figured
Oh.
out some of the biochemistry stuff.
Okay, well, we can talk about it after. I just want to do review first, and then we can revisit that topic. Jeez. And so basically what we can do is, so we can go through this reaction energy diagram. And so we have methane plus chlorine gives us chloroform and then hydrochloric acid. And so we see energy in to break our bonds. So there's our broken bonds. And then just how much energy we get back from making them. And so let's go ahead and do this. So what you would do is you have your standard table of bond energies. So you have to look this up. On the exam, I'll provide you the bond strengths. And we'll do 2 practice problems with this one. So let's do our class example. And so maybe I'll have you write the reaction and then I'll scroll back up to the table. And so we have methane plus water gives us 4 equivalents of hydrogen and CO2. And it says use the bond energies to calculate our delta H. So write this down. And so now I'll scroll up, if that's okay, to the bond energies. And so the only thing, so notice for CO2, if it's in a molecule like just CO2 itself, then you want to use this value of the CO double bond of 799 instead. All right, so I'll give you guys a second to try it. See if you can figure it out. What's being broken, what's being formed. So let's see, it should be, it's kilojoules per mole. So how are our calculations going? And so sometimes it's helpful to kind of draw it out so you can really see like what bonds you're breaking and making. And so I'm kind of just drawing it out. You know, you can even be really explicit, draw out your two waters. And then right, you can see, well, looks like we're changing everything, so we're going to have to break all those 4 CH bonds, break 4 OH bonds as well, and then we'll form 4 HHs. And then a CO2 or 2 CO2s, CO bonds, I mean. So let's walk through that. There we go. And so let's see how much energy we needed to break bonds. So how much was the CH bond worth? So 414, and then so times 4.
Is 1656.
I think 1656. And then we had our OH bonds. So how much was one of those worth?
The OH bonds are worth 464.
So 464, and then times 4 again. Do you have that number as well, or?
Yeah, it's 1856.
1856. And we can add them. I can pull up my calculator too. So what's our total energy in?
I got 3,500.
3,512 kilojoules, so that looks good. So any questions on this so far, what we've done? And so now let's compare our energy out. So bond formation. And so we said we made our 4 HHs. So what was one H bond worth?
436.
So 436, so times 4, 1744 kilojoules. And then we used our special value for that CO.
The 799.
Yeah, and then times 2,
1598.
1598. And so let's add those. And again, right, keep in mind, so this would be exothermic, so that should be negative 3342. Again, depending how you're talking, so either you're saying, right, it's releasing 3,342 joules of energy, or, right, it's negative enthalpies, so that also tells us it's exothermic, so just watch that. And then, so now let's add the two to give us our overall delta H then. So now plus my negative 3342.
So 170.
So that sounds good. So 170 kilojoules for that process.
And remind me, how do you know that the products are exothermic and that it's supposed to be a negative?
Just because you have to remember that bond formation is more thermodynamically favorable, at least. Well, we're just talking about enthalpy and bond breaking and making.
And to clarify, the 799 for the carbon dioxide bond is multiplied by 2 because it's a double bond?
Because there's two of the,
oxygen.
yeah, because the double bond already gives it the 799 strength, but yeah, there's two COs.
So why is the CO2 bond stronger than the one?
I'm not entirely sure, probably because like CO, if it's not by itself, it's doing other like pi back bonding, which is going to have weakening effects usually,
Oh, okay.
but. So let's do another one of these. I'll go back to my review page. Did you have a question?
This energy would come out as heat, you're saying?
Yeah, or it would require, in this case, 170 kilojoules. So then, right, it would be an endothermic reaction, so it would need some sort of energy input overall. All right, so back to our review. And so let's do another one of those so we feel good for our exam. And so now we're looking at this reaction. So ethylene plus bromine here. So this is a bromination reaction. And so then it makes this product. And so you are given the following values. So according to this, carbon-carbon is 611 kilojoules per mole. A carbon single bond is 348 kilojoules per mole. A bromine-bromine is 193 kilojoules per mole. And a carbon-bromine is 276 kilojoules per mole. Do you have answers?
Yeah, I got negative 96 joules.
So negative
Or kilojoules.
96 kilojoules. So let's go through that so everybody can be on the same page. So what did you get for bonds broken then?
So for the bonds broken, I got the bromine bond broke and the double carbon bond broke.
So bromine, so that was 193 and 611. So that's
They
four,
added up to 804.
thanks. 8, and then, so let's repeat that then. So bonds formed.
And the bonds formed were 2 bromine carbons and 1 carbon to carbon single.
So that was 348. So what did that come out to?
And that came up to be 900 even.
So 900. We can put negative, again, however you want to think about it. And then, yep, add those two together. So negative 96 kilojoules. Looks good there.
What was kind of tricky is I didn't realize that with the double bonds, instead of, like, if it goes from double bond to single bond, you don't just break one bond, you break the whole double bond and then reform the single bond.
Yeah. Excellent. Any questions on that? All right, so that should go well. And, oops, sorry, stepping on my cord. So I just wanted to say that we'll do this next quarter. So let's look at what we left off of your chapter. So the only thing we didn't cover was kind of this calorimetry stuff. But I just want to save it because a lot of it goes into like other math too and state change math. And it's not too hard, right? We did it. I'm not going to ask about it on the exam. So I think we'll just save it because otherwise I think we'll just lose too much other time trying to cover it. And then we can do it with state changes instead, which will work. All right, so let's go back to other problems. So let's do a little limiting reagent warm-up, and we'll do a harder one. So let's just start off with our good old Haber-Bosch process. So when 25 moles of H2 react with 12.5 moles of N2, what is the limiting reagent? So I see answer in the chat.
I got the hydrogen was the reagent.
So chat agrees with you, and so let's see. So let's just set up our ratio. So you said H2, so let's start with H2. So we have 25 moles of hydrogen, and you said this one was our limiting, so look at our mole ratio. So for every 3 hydrogens, we make 2 ammonia. And so how many moles of product did this end up being?
50 over 3, or
I
16.6 would be
16.6. And so if we repeat that, so the nitrogen, so 12.5. And now a 1:2 ratio though. So for every 1 mole of nitrogen, we get 2 of ammonia. So how many does this give us?
that gave us 25.
So 25 moles. So yes, looks like everyone agrees. This is our limiting reagent, so hydrogen. Excellent work, Chet, and in class. Good consensus. All right, so let's look at some more stoichiometry fun. So we can measure iron by precipitating out iron sulfide. I want to know how much iron nitrate was in my original sample if I reacted iron to nitrate with excess sodium sulfide to produce 12.34 grams of iron 2 sulfide. Load that up. And hang on.
And how much is referring to moles?
It doesn't say, so probably both. And so you want to start off, so your exam does not give you a balanced equation, so you have to start off your balanced equation. So at least try to get your equation written down, and then I'll probably go over it and then let you finish. So what did you get for your equation at least?
I got iron nitrate plus the sodium sulfide turns into iron sulfide plus sodium nitrate. And then there's a 2 on the sodium nitrate.
All right, that looks good. So now I'll let people finish up. So do we have answers? So what do we do first?
We have to convert the grams of iron sulfide to moles of iron sulfide. So I divided it by 88 grams.
Excellent. And then what do we do with that number?
Then we find the ratio between iron sulfide and iron two nitrate, right?
Yep.
Okay.
And yep, so they're just a 1-to-1 ratio, so yeah, that's easy. So now it's our same number. So we,
And I got 0.14 moles, I guess for both.
excellent. And then let's put this in a gram amount.
Yeah, then we need to convert the moles of the iron nitrate to grams of iron nitrate. So I multiplied it all by 180 grams.
180.
That might be wrong.
It just sounds a little low, but does someone have another number?
I did round a lot.
I got an even lower one, but I got 101.85 grams.
What'd you get, Camilla?
I got 0.1404.
0.14. Oh, but what about the mass though? Maybe I'm off.
I got 117.9. That's what I got too.
117 for the mass of iron nitrate?
I got 179.
Okay. I'll go with 179. I might be off in my notes then. Maybe I was dyslexic that day. Chat is also telling me 179, so. So times 179. And so did we get 25 grams about?
Yes.
And chat got that as well. And excellent. So 25 point. How many sig figs were we given? 421 grams. Questions on that one? It looks like that was good. Did that. All right, let's do, so there will be some structure to draw. So let's practice by drawing out bromate here. So see if you can draw the Lewis dot structure for bromate. Don't forget, so draw your formal charges, right, your number of electrons, formal charges, all that. Does someone want to draw it on the board for us? Or you could also just describe what you have drawn.
I can take a stab at drawing it on the board.
Okay, go for it. Hopefully those markers function.
We'll find out. There's 3 of them, so one of them has to work. Okay, good. So I put bromine in the center, and then 1, 2, 3, lone pair, oxygen, oxygen, oxygen. 1, 2, 3, 4, 5, 6, and then I said that there's more positive on the oxygen side and more negative on this lone pair side. So this would be
Well, remember the formal charges, you gotta do the individual.
Oh, I didn't do that one. I didn't do the formal charges then. But I did, this is the structure that I kind of came up with.
So that looks good, except we gotta add some formal charges to it. Especially because we have an overall charge.
I think all the oxygens would have a negative charge and the bromine would have a positive free charge.
Oh, so it would be opposite ways?
Check the positive, wrong way.
Or, I mean, positive too.
Yeah. So that's one structure. So, yeah, you want to draw a negative charge on each oxygen, positive on the bromine. Did you get something else?
Yeah, I drew a formula that minimized the formal charge, and I had it where bromine had that same lone pair still, but it had 2 double bonds to 2 of the oxygens and a single bond to the other oxygen.
So this is valid. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a little hypervalent, but that's fine, right? So you might want to note for these hypervalent, so 12 valence electrons that it's feeling.
On the exam, would you prefer one that fills the octet rule or one where it minimizes the formal charge of like that central atom?
So in this case, I'd want you to draw at least 2 structures, probably more, because, yeah, you want to get both of those ideas, because minimizing formal charges is pretty important, and then bromine is large, so it can go hypervalent, so this is a valid resonance structure. And then you could also include, right, the other permutation as well for this one, where you just have 1 double bond. So depending how hypervalent crazy you want to go. And then bromine still has a plus charge, right? 1, 2, 3, 4, 5, 6, so that leaves it. So this one, so all these are valid resonance structures. So on your exam, you want to draw, right, your resonance structures, show that they're all valid, show the double bond moving around. So this is fine, this is fine, this is fine. They're all fine, right, for different reasons.
Do you want us to also draw the like resonance structure with the dotted lines and stuff, where it's showing the possibilities, or just having a few examples is good enough?
Oh, either way. So yeah, if you like, yeah, understand what that means and like can draw that, that works. And then you can just show me with like kind of more with one structure-ish. But if not, right, just showing them the several structures.
So maybe like the most possible octet rule, the most possible minimizing charge, and then one that's kind of in the middle of those two.
Yeah, would be a really good bet. And it depends, right, what your molecule is and how many structures, but yeah, that's a good way to show. Any other structures for this one? So those are probably the best.
Yeah, can we do another, I can't think of an example, but can we do another one of the drawing the formal charges?
You want to do like another
Like another
molecule?
yeah.
So let's do, I think this one should work out. IF3, a negative charge on it. Maybe it doesn't. I don't think it has a charge. My bad.
I was gonna say, but I don't even
Yeah,
realize
sorry.
electrons.
Do we get a structure? So I want to put it on the board. Right.
Yes. I don't care.
So I had started off by calculating the valence electrons, just so I had an idea. For iodine, that is 7 loops, as you guys know. And it is also 7 gray, out of the electrical
one double bond.
That's what I got, one double bond.
Why'd you double bond them?
Just satisfied octet rule for this one, or an
So that
alternate.
no one is hypervalent.
Oh, it's okay if iodine. It's probably better to leave it hypervalent, because then if you do a double bond, that'll mess up your nice no formal charge, right?
Yeah, I was just trying to do multiple.
Oh, yeah, yeah.
Is that something that you want on the exam? Would you prefer that we, like, if we have one that's super nice and very concise like this one, would you prefer us to leave it as that one? Okay.
Yeah, yeah, so that's always right. So you also don't want to go too crazy, because you could try to draw it, right? But then, and I don't want to say like it's super bad if you put it on an exam or anything, but you just want to know, well, then your formal charge would change, and that's not ideal for fluorine, so then you could always, make a little note, like maybe not a good one. Do we want to do one more of these?
Yes, please.
All right, let's try, what about just good old sulfate? Someone want to put sulfate on the board, draw it out?
Yeah, I'll actually try that.
Okay, go for it.
Okay, so the first one I did was to minimize the formal charges. So I started with sulfur, or well, I guess I should do there's 32 electrons because you have each one of those atoms should have 6 valence and then the noticed that oxygen likes to have two lone pairs and two bonds because that equals a formal charge of 0 for it. So I put two oxygens like this and two of them with a single bond coming off of the sulfur that have a formal charge of -1, and the sulfur is super hypervalent but doesn't have any charges. And I was in the middle of doing one where the sulfur, where it's all single bonds and maximizes the octet rule on the sulfur. If you guys want me to try to do that, or if should I do that as
If
well?
you fulfill the octet rule, then for sulfur, then would it not have a formal charge? Because
It-
it's pulling equally in all directions?
But formal
That's
charge is
polarity.
different, yeah.
Oh, you're right. Never mind.
So you could also remove the double bonds here, put lone pairs here,
Yeah,
and then this becomes a +2, and these both become minus. To maximize octet rule on the sulfur.
You're right. Okay. Thank you.
Of course.
so that looks good.
Is there any other structure of those that look good?
So you could just make all the different
I guess one
permutations.
double bond
Yeah.
also.
So you could do the one double bond permutation and then rotate the double bonds around as well. So you want to draw, resonance structures. So at least 2 structures would be a good answer, and then, any others are always good.
On the exam for these types of questions, do you want us to include the, like the geometry, like the angles from that handout you gave us?
No, you don't have
No?
to,
Okay.
yeah.
Okay.
Alright, this might be kind of a confusing question, but, so like how we just did the one with the fluorine and how in the fluorine structure it had 6 like valence electrons like left over, okay? But it has technically 7 valence electrons. But then oxygen also, you put 6 like by itself. You know what I'm saying? Like I don't really understand like why they both have 6 lone pairs when they have a different number of valences. Like oxygen and fluorine, for instance.
Like you're talking
Yeah.
about this structure.
Yeah.
It just depends on the charges and everything too. So what kind of ended up happening, because this one was neutral, so that was kind of interesting. And so, right, it did end up with those 6 electrons around it and the 1 bond, right? Because that gave it a formal charge of 0, right? So 7 minus all those 6 electrons minus that 1 bond is 0. And we kind of see that with fluorine, that it tends to make 1 bond with things. And then with oxygen, so you notice it kind of depends, right, whether it's neutral or has like a formal charge of 0, right, where it makes that double bond. So oxygen likes to double bond typically, and then it just has the 2 lone pairs, or make 2 bonds, right? So either it double bonds, like in this case, or we see it with water, H2O. But then, because we have, right, a negative charge, the negative charge has to go somewhere. And oxygen is a really good place to put it, is kind of what it ends up being with these like organic structures, is that the oxygen ends up carrying the negative charge. And so that's why it appears to have the same amount of electrons as fluorine, which is right in this structure. But then we do have to put a negative charge on it, which is kind of signifying it's carrying more electrons than maybe it should be. But again, that's kind of what happens in the reaction chemistry. If you go into OChem, you'll notice all the time oxygen is always doing this sort of thing, going from this double bond to this resonance structure, and a lot of activity at the oxygen.
Sounds familiar with the fact that it's really electronegative.
Yeah, so that also, I mean, it's right there next to fluorine. And so that goes back to the hydrogen bonding too, where those are going to be hydrogen bonding. And
I do have a question. So should we not really go hypervalent over 12 electrons to theoretically, you could have all the oxygens double bonding to the sulfur and have this charge on the sulfur, but then it'd have like 16 electrons.
Yeah, so,
And that's not super realistic.
yeah, usually you don't see past like 12, yeah. But, well, unless we're talking about transition metals, but that would be,
Transition metals are weird.
yeah. But, yeah, that's a good observation and does seem to hold true. And because, yeah, you could have actually done the same thing with the bromate structures, done a funky one with bromine with all triple bonds, but yeah, for the same reason, it's also good to keep the the negative charge on the outer end, and then it can do things.
So negative charge likes to be on the outside and positive likes to be on the inside, kind
Probably charges like to be on the
of?
outside,
Just charges in general
yeah,
like to be-
so
oh,
they
okay,
can
got it.
access. All right, let's try the last type of problem. We kind of zoomed through this review, or maybe you guys are just fast. And so we'll look at this question. So we have our standard heat of formation for ethene here. Oops. So C2, H2. So we want to know what our standard heat of formation is, and so given the following set of information. Kilojoules, sorry. Carbon. 2. All right. So see if you can figure that out. do we figure out how we could add them up? Or any at least initial thoughts?
Well, the only how I started is the only equation that actually has methane in it is the first one, and in order to make it end up like the top equation, we want the arrow to be pointing towards the methane, so I reversed that equation and used it as like kind of a base for.
Okay, so we'll flip that. So that looks good. So CO2, oh, 2 CO2. It would help if I write it. Plus water gives a C2, this ethylene, plus oxygen.
And then I knew I needed to cancel out the CO2 on that side. So I just put the second equation down in the same way it was, because that makes the CO2 be on the opposite side.
And then
I didn't reverse it.
did you,
And I had to multiply everything by 2 as well, including the methane.
so 2 carbon, CO2.
For the last one, I did the same thing where I just put it down, but you don't have to multiply the H2O because there's only one H2O on the equation. But then I'm not so sure if it ended up working out or not.
So let's add it up. So this cancels, CO2 cancels. And then where are we at with oxygen? So 2 plus a half, so that would give us 5.5, right? So that does end up working out. So that's good. So did everybody follow that? And just like you said, right, use your big road mappers to kind of help you, because you got to figure out, well, I need my product, right? I need ethylene in there. And then it all did kind of fall in pretty nicely. All right, and then let's add it then. So we had to flip the sign. So 1299 is positive, and those are still negative. Just don't forget to multiply by 2. So I got positive 226.7. And looking for thumbs up. All right, excellent. And then if it was positive, did we say endothermic, exothermic?
It would be endothermic, because it requires energy.
Excellent. Endothermic. All right, should we do another practice of, so I just have another stoichiometry practice problem prepped.
Can you leave this one up just for
Oh.
like maybe a minute longer?
Yeah. I can scroll up a little if that helps. So just a reminder to check your grades. Don't forget your reading questions. Do not neglect those, or else you'll be, sad when you see your final grade. And then make sure you have all your assignments and you have grades for everything. I do have quite a bit of homeless papers, but I don't know if people have given up on the class, and maybe that's why they weren't unclaimed, but double check your grades and make sure your stuff is in there. Oh, and then make sure you sign up for next quarter. I don't know why they have it capped at 24 right now, but just sign up and we'll fit everybody in. Which is strange because they gave me 2 lab sections, so I don't know why they capped the lecture. I think that was a mistake.
Maybe they were supposed to be for the lab. Because this is the lab room on the 24th.
But they gave me 2 lab sections, so it should be 48 capped.
For lab maybe.
Are you still staring at this? All right, let's do one last problem, unless there are other requests. We'll have, so 2 equivalents of copper chloride plus 4 equivalents of copper iodide gives us, potassium iodide, sorry, gives us copper iodide plus, there we go, plus iodine. And so let's say 50.5 grams of copper chloride are reacted. And so I want both the molecules of iodine produced, and let's also do mass of iodine. And we'll do, if I recover 36.7 grams, what's my percent yield? So try that one out.
Percent yield of iodine?
Yeah, sorry. Oops. Oh, sorry.
Was the percent yield supposed to be higher than 100%?
Should be.
That would imply an error in the procedure.
It's just the recovered divided by the active, correct? By 100.
Or divided by their theoretical.
Theoretical.
I got 115%.
I don't think that's pure.
Or.
So let's start hearing what we have done. So what's the first step?
You take your grams of copper chloride and you convert it to moles.
Grams to moles was a good step. And then what's the molecular weight of copper chloride?
I got 134.452 grams per mole.
I also got that.
Excellent. And so we could punch that in and then
I got 0.38 moles.
0.38 moles. And so that's of our copper chloride. And then where did you go from there?
Then we want to ratio it over to just plain iodine. So it was 2 copper chlorides to 1 iodine.
That looks good.
And then that gives you how many moles of iodine you should have.
So what'd you get then? So 38 divided by 2, roughly.
I got 0.19 moles.
0.19 moles, roughly. So is that what people got for this one, roughly? So that looks good, of iodine. And so then it asked for, so we're at moles right now, but it asked for, so how do we go from moles to molecules then for our part?
Multiplied by the molecular weight of iodine. And remember that it's a diatomic, so you have to apply the molecular weight of iodine twice.
But that'll give us, because you said by the molecular weight, so then you're calculating mass though, right, of iodine?
So would you just take the 0.19 moles and multiply it by 127? Because it's diatomic, would it be whatever
Yeah,
127 is times 2?
yeah, so it'd be the 127 times 2,
Okay.
which I think is about 253. 0.81 grams. And then, so how many grams of iodine did that give us?
47.7 grams.
47.66 or 0.7 grams. But then what about the part A? So how do we get molecules though?
You would take that original mole value and multiply it by Avogadro's number, right?
Yeah, by Avogadro's number. So moles to molecules here. So 6.022 times 10 to the 23rd. And
I got about 1.13 times 10 to the 23.
that sounds good. And so that's molecules of iodine. 47.7 grams, so that looks good. And then, so if we got 36.7 grams, what's our percent yield?
I got 77.0%.
So that sounds correct, just,
Yeah,
With-
I got 76%. So it was just a rounding thing that made me different.
so about a 76% yield. So that looks pretty good. So that is all the review that I have prepared. And then, of course, if there are other questions, we can go over that. I can talk a little bit about the cell stuff at least, if people want me to. Just don't forget, so today we're doing makeups if you're a Thursday lab. If you can't make it today and you're the Thursday lab, please let me know. We can do it again on Thursday, but I need to know because I was trying to avoid doing that. But question?
Practice problem with molarity?
We can.
For like neutralizing that acid or something?
Yeah. So let's do. So if we have a 0.1 molar sodium hydroxide solution, and it took 15.78 milliliters to neutralize 2 milliliters of vinegar. Oops, I totally misspelled vinegar. Then how concentrated is the vinegar? And you can give it to me in weight per volume. And so that's weight as in grams per milliliter.
I might be mistaken in the information that we need, but do we need to know how many moles sodium hydroxide is needed to neutralize a mole of vinegar? Because I don't know that off the top of my head. I feel like that would be important.
You could write out the balanced equation. So I was trying not to give you too much information, but maybe you did need some help.
I did not know the formula for vinegar, so I will.
They're in a 1-to-1 molar ratio. How are we doing?
Slowly.
So let's start walking through it. So what do we do first here?
We can start by setting up an equation to convert find out how many moles sodium hydroxide we have. So that would be, of course, our 0.1 mole sodium hydroxide equals an unknown amount of moles over the, 15.78 milliliters, and we can convert that to 0.001578 liters.
So 0.01578 liters. And then we,
It's, 2 zeros.
Is it 2 zeros?
are you sure?
I think it's just one.
Oh. Well, then,
Uh-oh.
math is wrong by an order of magnitude.
So then times, so moles over liters of 0.1. So 0.1 times 0.01578. So then we had this many moles of sodium hydroxide.
That's as far as I got.
So 0.001578 moles. And so where can we go from here?
And I believe that's moles per milliliter, or is that just moles?
That's just moles.
Yeah, it's just moles.
The next thing I did was recognizing that it's that 1-to-1 mole ratio. I'm not sure if that's the correct way to do it, but recognizing that there's that same amount of moles of acetic acid or vinegar.
Yep. So that's the next step. So I probably should have drawn out the math, but maybe it's easy enough to see. So they're in a 1-to-1 mole ratio. So I just rewrote the answer. So now, what do we do with this information?
We can use that to find the mass of vinegar. So I can write it down and look. I found that the atomic weight was 60.05 grams per mole.
Yeah, that sounds correct.
We multiply those together. We get about 0.0948 moles.
Or grams.
Grams, I mean.
0.0948 grams of vinegar.
And then you just divide that by the 2 milliliters.
Yep. And so now we know how many grams of vinegar we had in our original 2 ml sample. And so our weight per volume, we just divided by 2. And then we can convert it to a percentage. So times 100, so about 4.73% weight per volume. So that was a good practice. You have a question? Any questions on this one? Are we all okay? Cool.
And you just divide it by 2 milliliters, right? You
Yeah.
don't convert the milliliters to liters?
No, because the weight per volume can be grams per milliliter, so I just
Okay.
left it.
So as long as you have the correct units,
Yeah,
you could use whatever.
exactly. Excellent. Any other burning review questions? So I didn't want to leave people hanging on the biochem stuff and some of the questions, because y'all had good questions on that. So we could at least briefly talk about this, and then you can, of course, explore more on your own as well. And so part of the problem when we were talking and looking at our individual bonds, especially our bond breaking, is right now we're only talking about delta H, right? So we're only looking at our change in enthalpy, aka we only are focused on heat. But we haven't gotten there, and so the next part of the issue is that really we want to look at what's called delta G, and so this is what we'll be exploring kind of second quarter, so this is a good preview. So delta G is Gibbs free energy, and so it's more like the available energy. And so the next question is, well, okay, when we look at this reaction though, so now let's just look at, right, converting some sugar and adding oxygen to it, and of course, right, we produce CO2 and water. And well, that reaction, if we just take that on a chemical level, right, so if we obviously, like, we could do the combustion, and that would, we could also calculate the enthalpy change, but in this case, they've given us the delta G, and so this releases a lot of energy, right? So there's a lot of energy stored in that reaction. Of course, what's really different, right, about how the body breaks stuff down versus the chemical reaction is we don't just do this, right, in one step in your body of just like burning something like we do in the chem lab. And so that's what's really either fascinating or painful about biochemistry.
It's painful. I can tell you from experience.
It
So-
seems cool to think about. It seems not so cool to math about.
Agreed.
Well, and what was also kind of fascinating is like when I was trying to research better answers, it's like people are still trying to figure out the exact thermodynamics of the cell too. And so this is just a big overview, like, so this is the extremely big overview of metabolism and, right, how you break stuff down. But then all of these little steps, right, have tiny, 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 tiny portions. And so let's look at that, kind of what goes on. And so what happens in your body is that it tends to couple reactions. So it's going to couple a reaction that is not favorable. So something, we'll later learn this, that if your delta G is positive, that means it's not spontaneous, so that's not going to go. But if they couple it with another reaction, such as like your ADP reaction that is favorable, then that's how each little individual step gets powered. And so one example of this, and so I chose this little example because you might be familiar with ATP, and so that's considered, right, your energy molecule in the cell. And so why it's considered that way is because this hydrolysis reaction is pretty favorable, and so it has that negative delta G. So this step, for instance, so this adding this phosphate group to our glucose, so this is not spontaneous, but in our cell, so this is coupled at one little point, and so that allows this little portion to go together. And so this is just one tiny example. So this is repeated, you know, over and over and over again, billions of times in the cell. So if you are intrigued about this, what is beautiful is there's now an OpenStax organic chemistry that just went live. So if you really want to get into it and look at it more, way down at the back is all the biomolecules, so looking at these pathways, so right, looking at all of those in depth and the chemistry behind them, so you could get an appreciation of that. The other thing is, so right when we were talking about it and looking at our delta H, we were just looking at our standard values, right? So we said that those were standard conditions with 1 molarity. So obviously your cell is not a standard condition. I don't think I have the paper handy, but there's a lot of research still being done of like trying to mimic the cell and like figure out the all these entropic values. So they don't have a lot of enthalpy calculations necessarily, so this is still ongoing research to figure out exactly what the thermodynamics of every little step is. So there's a lot of detail in there, but I at least wanted to touch on it and come back to it since you asked, but it's
I know in glycolysis, which is the very first step of like turning a sugar molecule into a bunch of energy that you can use, your cell actually has to expend 2 ATPs in order to gain 4 ATPs for a net of 2 ATP. And then that smaller molecule that the glucose is chopped into can be used again in other more favorable
yeah.
reactions.
Yeah, I mean, that's where it goes. So you could drive yourself
I
either.
have driven myself crazy.
Well, see, that's good. So now you know where to go. But that's the short of it. So, all right, that's
I
probably.
luckily didn't have to find how many kilojoules per mole of energy was created.
Yeah. Anyways, thank you guys for an awesome class. So make sure you sign up for next quarter. And I'll see hopefully the Thursday half so we could do our checkout and lab final today. And then otherwise everybody on Thursday for final.
I think so.